picture this.
Yeah.
You're in a spacecraft, right? You've somehow managed to navigate your way through the cosmos.
Okay.
And you pull up right to the very edge of a black hole.
Oh, not a great vacation spot.
No, the ultimate abyss. So my question is, what actually kills you first? And maybe more importantly, how can physicists sitting safely in their offices here on Earth possibly know the answer to that?
Right.
Because we have never, ever sent anyone or anything anywhere near one.
It's basically the ultimate locked room mystery. The short answer to what kills you first is tidal forces.
Okay.
But the longer, much more fascinating answer depends entirely on the black hole's mass, your exact distance from it. And, well, there's a really crucial distinction between just crossing the event horizon and actually reaching the fatal central region.
Which is exactly our mission today. We're doing a deep dive into this absolutely massive central question. It's based on our sources, including Neil deGrasse Tyson's book, Death by Black Hole.
Yes.
And over the next 15-ish minutes, we're basically going to explore how science turns light, motion, matter, and gravity into reliable knowledge of a universe that is, mostly distant, invisible, and just completely extreme.
It is a huge mandate.
Yeah, the roadmap is packed.
Huh?
We're going to look at how science actually knows things, the sheer scale of the cosmos, light, spectra, how gravity and orbits work.
And stars and element formation.
Right. And planets, habitability, the search for extraterrestrial life, plus cosmic hazards.
Yeah.
And then we'll get into the anatomy of black holes, the mysteries of dark matter and dark energy, and wrap up with how science clashes with culture.
So we're looking at the foundational rules of reality, basically. From the smallest subatomic particles to the largest gravitational structures, and ultimately to the darkest parts of the cosmos that we can't even see.
Right, so let's unpack this.
Yeah.
Because I think it's incredibly easy to just stare up at the night sky in total wonder.
Yeah.
But at some point, we have to ground this in the reality of the scientific method.
We do.
Like, how do we actually know any of this? If I'm a biologist, I can just, put a cell under a microscope.
Mm-hmm.
But astronomy feels like being a detective at a crime scene you can never, ever touch. You could put a star in a beaker.
Yeah.
So how do you know what happened?
I love that analogy, but you have to remember, a good detective doesn't need to actually witness the crime to know exactly how it played out.
Okay.
They look at the evidence left behind. And in astronomy, that evidence is light and gravity. We have to start by realizing that science isn't just a fixed warehouse of facts that you memorize from an encyclopedia.
Right.
It is a rigorous method. It's this continuous loop of observation, measurement, prediction, and correction.
So when you can't touch the evidence, what exactly are you measuring?
We measure what we label as observed phenomena. We track the trajectories and motion of stars over decades. We analyze the spectra, which are like the specific fingerprints of light coming from distant galaxies.
Like barcodes, basically.
Exactly like barcodes. We gather radiation across multiple wavelengths, and we measure the precise gravitational effects that massive objects have on their surroundings. And then we take all of those physical measurements and we combine them with mathematical models.
Okay.
And that is how we can confidently infer the properties of objects that are light years out of our reach.
Which really forces us to confront the sheer scale of what we're looking at, right?
Yeah.
Because modern astronomy has this funny habit of constantly demoting us.
It really does.
Like first, humanity thought Earth was the absolute center of everything.
Right.
Then we realized, oh wait, we're just a planet orbiting a star.
Yeah.
And now we know we're just one tiny planet around one very ordinary star in a galaxy of billions of stars, which is just one of an enormous number of galaxies.
Yeah.
It's called the Copernican principle. It basically just says you are not special.
Well, physically, no, we aren't in a privileged or central location. But we have to be incredibly careful not to conflate that physical smallness with human insignificance.
That's a good point.
Yeah, because physical smallness and moral value, they answer completely different questions. The staggering scale of the cosmos might, produce humility, but it doesn't erase our responsibility for life, for art, or for the pursuit of knowledge right here on our pale blue dot.
Right. And speaking of the building blocks of that dot, the source material gets into the rules governing all this matter.
Mm-hmm.
Specifically, the sheer weirdness of particles and antimatter.
Oh, yeah, antimatter.
The idea that there's this, mirror version of ordinary atoms, and if they meet, they instantly annihilate, converting their mass into pure energy. It sounds completely like science fiction.
It does.
So does this mean we are close to building, like, limitless sci-fi antimatter engines for our spacecraft?
I hate to burst the sci-fi bubble, but no.
Oh, man.
I know antimatter is entirely real, but macroscopic storage, like keeping a usable amount of it stable, is extraordinarily difficult.
Why is it so hard? Can't we just, I don't know, put it in a really strong tank?
Because of that exact annihilation property you just mentioned?
Right.
Yeah, the moment antimatter touches the ordinary matter that makes up the walls of your storage tank, it violently destroys itself.
So it just blows up the tank.
Instantly. So to store it, you have to suspend it in a perfect vacuum using these incredibly complex magnetic levitation field, so it literally never touches anything. Plus, it requires vastly more energy to produce even a tiny fraction of antimatter in a particle accelerator than you could ever yield from it. So it's a fascinating physical reality, but it's definitely not a limitless power source.
Okay, so no warp drives anytime soon. But the laws governing that antimatter brought up something else the sources emphasize, which are physical constants.
Yes.
Things like the speed of light. Because I always thought of the speed of light as just, a really fast speed limit, like a cosmic traffic law we might eventually figure out how to break.
That is a very common way to look at it. But the speed of light in a vacuum isn't just some engineering hurdle. It is the causal structure of relativity itself.
Wait, what does causal structure actually mean?
Think of it as the speed of reality, the speed of cause and effect.
Okay.
If the sun were to magically disappear this exact second, Earth wouldn't go dark instantly.
Right, because the light takes time to get here.
Exactly. But we wouldn't even lose the sun's gravitational pull instantly either. It takes about 8 minutes for both light and gravity to travel that distance. So for those 8 minutes, in our reality, the sun is still entirely there.
That is so wild to think about.
Right. Relativity is what we label as a theoretical framework, but it governs the entire universe. The apparent universality of these physical laws is what allows us to trust that the physics we test in a lab on Earth perfectly applies to a galaxy a billion light years away.
And that light is really our primary messenger. It blows my mind how much we decode just by catching photons. Like, telescopes aren't just giant magnifying glasses for our eyes anymore.
Not at all.
We're looking across the entire electromagnetic spectrum: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray.
And how we process that invisible information is where public misunderstanding often happens. Oh, you mean like with those space photos?
Yes. You've probably seen those breathtaking, incredibly vibrant images of nebulas and galaxies from telescopes like Hubble or Webb.
Oh, absolutely. They look like glowing cosmic tie-dye.
Exactly. But people often hear the term false color imagery and think astronomers are just photoshopping space to look pretty or dramatic.
Like you're just making it up.
Right. But that's entirely wrong. It is an observed mapping of data. We are taking invisible wavelengths, like X-rays or infrared light, which human eyes literally cannot process, and we're translating them into visible colors.
Okay, so it has a purpose.
Yes. We assign a color to a specific wavelength to help us visually see the physical conditions of that gas cloud, like its temperature or the presence of specific elements.
So it's basically just data visualization.
Yeah,
It's exactly like using a thermal camera to see where heat is leaking from your house in the winter.
Yes.
You're assigning the color red to the heat leak, even though heat itself doesn't actually look red to the human eye. That is a perfect analogy. You are making the invisible visible so you can analyze it. And when we look at those extreme conditions, the sources talk about fire and ice in space, but we have to completely redefine those terms.
Because it's not normal fire.
Right. When we talk about fire in a star, it's not ordinary chemical combustion. You can't put out a star with a giant fire extinguisher.
That would be a very big fire extinguisher.
It would. A star is plasma. It's an ionized state of matter, completely shaped by intense electric and magnetic fields. And astronomical ice doesn't just mean frozen water cubes either.
Where else could it be?
It could be frozen methane, ammonia, or carbon dioxide.
Well, but, telescopes, no matter how good they are, can only see what shines or what blocks light. How do we find the architecture of the universe that doesn't glow?
Gravity.
Right. We have to stop looking for light and start looking for gravity, because gravity shapes everything. Let's start on a smaller scale, right in our own orbit. I want to bring up astronauts.
Oh, this is a good one.
Yeah, because we see them floating around the International Space Station, doing flips, eating those floating blobs of water. It instinctively looks like they have traveled completely beyond gravity.
This is one of the most persistent myths in space exploration. Astronauts in low Earth orbit are not beyond Earth's gravity at all.
Really?
Yeah, the gravity up there is still about 90% as strong as it is right here on the surface.
Wait, if there's still 90% gravity, why on Earth are they floating?
Because they are falling. An orbit is simply continuous free fall. The spacecraft is moving forward so incredibly fast, about 17,500 miles per hour, that as gravity pulls it downward, the curve of its fall perfectly matches the curvature of the Earth beneath it.
So they aren't floating in some zero-gravity room. The space station is basically a roller coaster dropping down a hill that never, ever ends.
Exactly. The astronauts are floating because they and the spacecraft around them are falling together at the exact same rate. They constantly fall and they constantly miss the central body.
That is simultaneously terrifying and amazing.
Oh.
Now, if we scale that gravity up, the heavy lifters of the cosmos are, of course, the stars themselves. We've all heard that incredibly poetic Carl Sagan quote that we are made of star stuff.
It's a beautiful thought, and it is fundamentally true. It's driven by the theoretical mechanics of stellar evolution and nucleosynthesis.
Okay, break it down for me.
So, a star is essentially a delicate billions of years long balancing act. Gravity desperately wants to crush the mass inward, while the immense nuclear pressure from the core pushes outward.
Right.
And inside that core furnace, lighter nuclei are smashed together and fused into heavier ones. However, we should be precise here. While heavier elements like the carbon in your cells and the iron in your blood are absolutely forged in stars and exploding supernovas,
Yeah.
most of the hydrogen in your body traces all the way back to the early universe, long before the very first stars even ignited.
Oh, wow. So we have some really ancient stuff in us. And when those stars finally run out of nuclear fuel, that delicate balancing act fails.
Right. Gravity wins.
The star collapses and dies, leaving behind some of the strangest, densest objects in the universe. Compact objects like white dwarfs, neutron stars, and black holes.
And which one of those you get is a category entirely dependent on the original star's mass, its internal structure, and its specific evolutionary history.
Okay, so we have these dead stars, but we also have living stars surrounded by planets made of that recycled star stuff. Let's look at those planets in our search for cosmic neighbors.
Okay.
Because we are constantly hearing news about astronomers finding Earth-like exoplanets or discovering habitable zones.
Yeah, and we need to tread very carefully with that vocabulary because the terminology often misleads the public. When astronomers assess an exoplanet and declare it habitable, that is a completely model-dependent assessment.
So what does it actually mean?
It simply means the planet is orbiting at the right distance from its star, the Goldilocks zone for liquid water, to potentially exist on its surface. It absolutely does not mean the planet is currently inhabited by living things.
Right. Finding a puddle of water does not automatically prove a fish lives in it.
Precisely. The rigorous fields of astrobiology and the radio searches for extraterrestrial intelligence are vital, exciting science. But any specific claims about having actually found alien civilizations right now, those strictly remain speculative.
And even without aliens, the universe is incredibly dramatic. We tend to think of space as peaceful and silent, but it is deeply hazardous.
Oh, very.
We've got chaotic orbital dynamics, massive asteroid impacts, exploding supernovas, and gamma ray bursts that could, fry a planet's atmosphere in a matter of seconds.
The universe is definitely a violent place, but when astrophysicists use the word chaos to describe orbital dynamics, they don't mean nature has lost its mind.
Right? It's not just random.
No, it doesn't mean there are no laws. In mathematics, chaos simply means the outcomes are highly sensitive to complex gravitational interactions. The laws of physics are still perfectly in charge.
Okay.
It's just that predicting the exact long-term outcome over billions of years becomes impossible, because even a microscopic change in a planet's starting position drastically alters its future orbit.
So let's turn to the ultimate hazard, the invisible monster we use as our hook at the very beginning, the black hole.
Here we go.
It is the extreme of the extreme.
Yeah.
But before we talk about dying in one, we have to clear something up because Hollywood movies almost always get this wrong.
They usually do.
Black holes are not giant cosmic vacuum cleaners, right?
They are definitely not. They do not just wander around sucking up everything in the galaxy. Gravity is still just gravity.
Right.
If you replaced our sun right now with a black hole of the exact same mass, Earth would not get sucked in.
We wouldn't.
No, we would just keep orbiting it in the exact same path we are on right now. I mean, it would be very cold and very dark, but our orbital mechanics wouldn't change.
That is strangely comforting. But what about the edge, the event horizon? We often picture it as a physical wall or like a a black sphere you crash into.
That's another major misconception. The
Yeah.
event horizon is not a solid material surface like the crust of a planet.
Then what is it?
It is simply a causal boundary in empty space. It's the mathematical threshold where the escape velocity required to pull away from the black hole exceeds the speed of light. Because the causal structure of the universe dictates nothing can go faster than light, nothing can return once it crosses that invisible line.
Okay, but what about those incredible images of active galaxies shooting out massive, glowing jets of material? If nothing escapes, where are those jets coming from?
That is a crucial distinction. Those powerful jets emerge from what we label as observed, highly magnetized matter swirling in the accretion disk outside the black hole.
Ah, outside.
Yes, that material gets superheated and blasted away by magnetic fields just before it crosses the horizon. The jets do not come from inside the black hole. Nothing escapes the inside.
Okay, so let's go back to our opening scenario. What if I stay safely away in my ship, but I watch a friend of mine fall in? What do I actually see?
Well, popular culture sometimes says you would see your friend permanently frozen there forever, like a photograph.
Right, I've heard that.
But that's not visually accurate. Because of extreme gravitational time dilation, the light reflecting off your friend gets increasingly delayed. But more importantly, it gets redshifted.
Wait, what does redshift actually mean in this context? Are they literally changing colors?
Yes, visually.
Seriously?
Yeah, as they fall deeper into the gravity well, the light waves bouncing off of them have to fight so hard to climb out to your eyes that the waves actually get stretched. And in physics, longer wavelengths of light are redder.
Oh, wow.
So as they fall, their image would shift into the red, then stretch into invisible infrared and become impossibly faint. To you, the distant observer, they wouldn't look frozen. They would quickly fade to black.
But what about for them?
For your infalling friend, their own experience of time remains completely finite and normal to them as they fall.
Which brings us to their actual physical experience.
Mm.
Death by black hole. You mentioned tidal forces earlier. Explain spaghettification.
Spaghettification is based on theoretical tidal force calculations. Gravity obeys an inverse square law, meaning it gets significantly weaker the further away you are.
Right.
If you fall into a black hole feet first, your feet are physically closer to the center of mass than your head is.
Right.
Therefore, the gravity pulling on your feet is vastly stronger than the gravity pulling on your head.
So it literally stretches you out.
Yes, you are stretched lengthwise and squeezed sideways, like a piece of spaghetti.
Yikes.
But here's the crucial distinction that answers our opening question. The experience changes drastically depending on the mass of the black hole. Near a smaller, stellar mass black hole, the gravity gradient is incredibly steep.
Meaning the difference between your head and feet is huge.
Exactly. The change in force over just 2 meters is so sharp that you are violently torn apart outside the event horizon.
So you die before you even cross the threshold.
Correct. But near a supermassive black hole, like the ones at the center of large galaxies, the tidal forces at the event horizon are much gentler. The gradient is smoother. A traveler could actually cross the event horizon completely intact.
So they survive.
Well, briefly.
Oh.
Yeah, they survive crossing the horizon, but they are still on a one-way trip toward the fatal central region where the curvature of space-time becomes infinite. They will eventually be spaghettified. It just happens later on the inside.
Got it.
And I must emphasize, any detailed claims about what they actually see or experience deep inside that interior, those remain purely speculative because no information can ever come back to us.
Wow. Okay, so we've talked about the invisible things we can find using gravity, but let's pull back and look at the absolute biggest picture possible, the stuff we can't see that makes up almost everything, dark matter and dark energy.
This is perhaps the greatest humbling of modern science. Our current standard cosmic inventory, which is a model-dependent reconstruction based on all available data, tells us that ordinary matter, everything we've talked about so far.
Stars, planets, gas clouds, you, me, black holes.
Right, all of that makes up roughly 5% of the universe.
5%, that's it.
That's it. About 27% is dark matter, and roughly 68% is dark energy.
The names make them sound like two sides of the same coin. Like if dark matter is the invisible cosmic glue holding galaxies together, Is dark energy basically a cosmic wind blowing everything apart? Do we actually know what's generating that wind?
That is a great way to visualize the effects, but it is vital to stress that dark matter and dark energy are not the same substance at all.
They aren't.
No, they're entirely different phenomena. Dark matter acts like gravity. It pulls things together. We infer its existence from observed gravitational lensing.
Which is when massive objects bend light.
Exactly. A massive cluster of dark matter bends the light of galaxies far behind it, distorting the image like looking through the thick base of a wine glass. We also measure how galaxies spin far too fast to be held together just by the glowing matter we can see. But actually, identifying the exact unidentified dark matter particles, that remains speculative.
And what about measuring the cosmic wind? Dark energy.
Dark energy acts like anti-gravity. It pushes the fabric of space apart. It is simply a placeholder name for the completely unknown cause of the observed, accelerated expansion of the universe.
So we don't know what it is, we just see it happening.
Right. We measure that expansion by observing the light from distant, exploding supernovas, using them as standard distance markers, and seeing that they are moving away from us faster than they should be. We can measure the expansion, but we really don't know the engine driving it.
It's incredible how these mind-bending concepts bleed into our public imagination.
Yeah.
We see it in movies, in cultural beliefs, in how we talk about our place in the cosmos.
Yeah.
But people often want absolute fixed answers. They want science to be a religion of facts.
And that leads to a frequent conflict between empirical measurement and non-empirical claims. Science is completely comfortable saying, we don't know yet. That's exactly what the term dark energy is, an open admission of a mystery. True scientific literacy means understanding numbers, understanding probabilities, and embracing uncertainty, rather than demanding final, fixed, unchangeable answers to every cosmic question.
Which brings us to our verdict. We've gone from the very nature of observation to the violent deaths of stars to the invisible forces tearing the fabric of reality apart. Neil deGrasse Tyson's book remains a powerful, wide-ranging introduction to this cosmic literacy. It really teaches you how to think about the universe.
It absolutely does. However, because science is always progressing and correcting itself, to get the most out of it today, those older examples must be updated using current evidence.
Like what?
For instance, incorporating modern 2026 cosmic maps of unseen mass, and the recent massive breakthroughs in gravitational wave astronomy, which actually let us hear black holes colliding through ripples in spacetime, rather than just looking for their light.
Now, before we wrap up, we need to make it clear that this has been an independent deep dive into the source material. This is an independent Cosmora HQ book overview, and not an official or complete audiobook. We highly encourage you to lawfully access the published collection for Tyson's complete prose, his fantastic humor, and his detailed argumentation. And if you enjoyed this journey, please invite others, subscribe, comment, and share.
We've talked a lot today about what we can see, what we can measure, and what remains deeply hidden in the dark.
Which leaves us with a final thought to mull over. If our entire understanding of the universe relies on the light that manages to reach our telescopes, what happens billions of years from now when dark energy expands the universe so fast that the light from other galaxies can no longer ever reach Earth? Will future civilizations look up at a completely empty, pitch-black sky and logically but wrongly conclude they are the only things in the entire universe?
It's a haunting possibility. And it's exactly why we have to be so careful with our methods today. When the universe is mostly beyond direct human reach, which combination of observation, theory, and doubt should earn our trust,